telescopes that participated in this observation. So this is the IRAM telescope in Spain. Here we have ALMA in Chile. We also use the APEX telescope in Chile as well. Here we have a large millimeter telescope in Mexico. The submillimeter telescope in Arizona. The SMA and the JCMT in Hawaii also participated, and finally the South Pole telescope. So these are the telescopes that participated in the first full array observations that were carried out in April of 2017. We also observed in the beginning of 2018, and we also plan to observe in the beginning of the next year. So these are the original telescopes that were part of this first observation, but we do expect to be able to observe with potentially 3 more telescopes in the beginning of 2020. So obviously we're very excited that we're already able to create an image using just these telescopes. So we have 8 telescopes in 6 different locations on Earth, but we always are very well aware that as you add more telescopes each time, we do expect that the image will each time always be improving. Telescopes are clearly not enough. We also need a lot of people that are spread around the world. This image was taken at our last collaboration meeting. This was in November of 2018. The collaboration meeting was held in the Netherlands. Obviously, not everybody can come to all of our collaboration meetings, but this is a very good sample of the people that are involved. One thing that I find particularly interesting about this image is that when this image was taken, we had all already seen the image, and we were all very, very excited that all of our hard work had finally paid off and that this experiment had actually worked. So the first time that I saw the image was June of 2018, so in November we had seen many of these images already. And so I'm also contractually obligated to show you the EHT board institutions, as well as the EHT affiliate institutions, and of course the EHT funding agencies, which are also spread around the world, as you can see. So the primary goals for the Event Horizon Telescope are to test key predictions of general relativity with horizon scale imaging. We would also like to probe accretion and jet physics. And finally, we would also like to be able to connect with variability studies, specifically trying to understand the causes of the flaring events that we have observed, already observed with, for example, Sag star. So first, I would like to take a little bit of time to explain what it is that you're actually seeing when you look at the image that was published in April of this year. So the first time that somebody tried to calculate what you would see if you were to look at a black hole was in 1973. That was a paper by the physicist James Bardeen. And a few years later, there was a second paper in 1979 by Lumet. The image that I'm showing you here is, that image is from that original paper from 1979. And what Lumet calculated in that paper is what you would see if you were to look at a black hole, and if somebody was behind that black hole shining a flashlight on it. And what he found is that the observer would see a bright ring, which would encircle a dark region. That dark region is what we now call the black hole shadow. I also have a video that I hope will illustrate this concept a little bit better. So the green circle that you see here, this is the event horizon of this black hole, and all of these red and blue lines are photons. And this is a simulation, or results of a simulation, and we'll see how the trajectory of these photons will be affected by the presence of the gravitational field of the black hole. So let's go ahead and play that. So as you can see, all of the blue photons will fall into the black hole, and all of the red photons will escape to infinity. And it's the lack of light that is created by these blue photons that is what we call the black hole shadow. And the point that I wanted to emphasize here is that if you were to compare the size of all of these blue photons right here, if you were to compare that to the size of the event horizon, you can see that the black hole shadow is about 2.5 times larger than the event horizon of the black hole. And that's really important because when you look at the dark region in the image that we published in April, it's always important to remember that what you're seeing is not the event horizon, but you're seeing the black hole shadow, and that the event horizon would be significantly smaller than the shadow that you are seeing. For those of you who are interested in the details, I do have also the actual values here. So the radius of the black hole shadow for a Schwarzschild black hole is expected to be the square root of 27 gm over c squared. I've set g and c to 1 here. the event horizon for short-jaw black hole is 2 GM/c², just for you to get more precisely the difference in sizes there. So there are 2 primary event horizon telescope targets. The black hole in the center of our own galaxy, Sagittarius A star, or Sag A star for short, and also the black hole in the center of M87. So I just have a very quick summary of both of these black holes here for you. The mass of the black hole at the center of our galaxy is 4.3 times 10 to the 6 solar masses, with a distance of 8.3 kiloparsecs. The black hole, the center of the M87 galaxy, has a mass of 6.5 times 10 to the 9 solar masses and a distance of 16.4 megaparsecs. So the point here is that the black hole in the center of our own galaxy is about 1,000 times smaller than the black hole in the center of M87, but also is about 1,000 times closer to us. And so these 2 factors of 1,000 approximately cancel out, because obviously they're not exactly 1,000. And we do expect that the size in the sky from our point of view for both of these black holes will be the same. So specifically, the expected black hole shadow size for Sag A star is 50 microarc seconds, and for M87 is 40 microarc seconds. And as you've seen, 40 microarc seconds has in fact been confirmed by our observations. So the plot over here I think is very interesting because it summarizes all of the potential sources that we know of that the EHT could potentially try to image. And so what I'm comparing here is on the y-axis I'm showing you how bright these sources are at 1.3 millimeters, which is the wavelength that the Event Horizon Telescope observes at. And the x-axis is showing you the resolution that the EHT would be able to get. So things that are more towards the left will have a higher resolution, and things that are higher will be brighter. So Sag A star and M87 are very clearly the 2 best sources for us to use for this. But all of the sources in the purple triangle here on the top right, those sources are definitely bright enough for us to observe and might still be very, very interesting for us to observe. We just won't be able to get horizon scale resolution for those sources. So we've actually already observed all of the sources in the purple triangle as well. So we do hope that we'll be able to soon put out interesting images of these sources that will help us understand more about accretion, because these sources, most of them are AGN, so they're very active, whereas Sag A star and M87 are not active. They have a very low accretion rate. So these are 2 different categories of accretion flows. And so it's very useful for us to be able to observe both of these, even though we won't be able to get high enough resolution to see the black hole shadow of the sources in this purple triangle. So I've already mentioned that we're observing at 1.3 millimeters, and that is very important, but also very challenging. So I wanted to kind of walk you through the reasons why we chose to use this wavelength. So first, the peak of the millimeter to infrared emission for Sag A star is at close to 1.3 millimeters. The atmosphere on Earth is also transparent to this wavelength. The interstellar medium effects are subdominant, and finally, we expect that for low accretion sources like Sag A star and M87, we expect that the accretion flow will become optically thin at 1.3 millimeters. So what you're seeing here, this is the result of a GRMHD simulation for a low accretion black hole, but you're looking at this black hole at 1 centimeter right now. And so if we were to build an instrument that would observe at 1 centimeter, we would be able to learn more about the jet and the accretion flow, but we would not be able to see the actual black hole shadow because the accretion flow would be obscuring our view. So if we instead were to go to a shorter wavelength, you can see how as you go to a shorter wavelength, the accretion flow becomes optically thin, and this ring here, this is the black hole shadow. And now we've obviously zoomed in, and I'm letting the simulation evolve as a function of time, but hopefully you can still see that even though the turbulent accretion flow is creating a lot of variability in this image, hopefully you can see that there is a ring here that remains fairly constant as a function of time, despite all of this other variability that you're seeing. And so that is what we are trying to measure with the Event Horizon Telescope. So I think it's really important to really go into the details of how our data works, so that everybody here can leave today fully understanding what are the limitations in our imaging algorithms, and really understanding which parts of the image you should really trust and which parts you should be a little bit cautious about. So with that in mind, I hope you will bear with me as I delve into the details of very long baseline interferometry. So the way this works is that each pair of telescopes will observe one particular location in Fourier space. So interferometers do not observe actual images, but they observe the two-dimensional Fourier transform of the image. And so specifically, as I mentioned, each pair of telescopes will observe one specific location in the Fourier domain. And what is interesting is that the distance between the telescopes will determine which frequency you can observe in the Fourier domain. And so the distance between the telescopes, so if the telescopes are farther apart, you'll be able to observe a location that is farther from the center of the Fourier domain. And that's really important because in interferometry, for us to be able to get a higher resolution, we really need to be able to probe higher frequency components in the Fourier domain. And what that means is that we need to be able to probe locations in Fourier space that are farther from the center of the Fourier space, right? So each time we have two telescopes that have a very long baseline between them, we can probe frequencies that are higher, and therefore we can probe more fine-scale structure in our image. So as the Earth rotates, each pair of telescopes will observe a slightly different location in Fourier space. And you can also see that now we have several other telescopes that are also joining our observation because they can now see the imaginary source, which is essentially you guys right now. So you can see how by waiting for the Earth to rotate, we can probe more regions of Fourier space. But even after 12 hours, of observations, we still have a lot of empty space here. This is really the best that we can do with the array that we used in 2017 for M87. And so as you can see, we can get a lot of information, but there's definitely a lot of information missing. And so if you were to try to use this data to reconstruct an image, you can see how your algorithm would have to guess, for example, what is happening over here, just as an example. And so now let's move on to the actual data. So this is the data that was used to make the image that was published this year. We have 4 different days of data. For M87, this is just one day as an example. The plot I'm showing you over there, that is the same plot that you just saw, but now I've actually labeled each of those little curves with the 2 telescopes that contributed to that baseline. And on the right here, I'm plotting the exact same data, but I'm plotting it in a different way. So instead of showing you the two-dimensional distribution in the Fourier domain of where these data points are located, I'm instead only going to show you the amplitude of the complex Fourier component as a function of the distance from the center of Fourier space. So for example, I pressed the wrong button. So for example, these blue points right here correspond to these 2 baselines that you're seeing right here. And the reason why I'm doing this is I want you to be able to see how the amplitude of the Fourier component evolves with baseline distance or spatial frequency. This dashed gray line here, this is just to guide your eye. That is what the visibility amplitude or the amplitude of the Fourier component would look like if you were looking at something that was a very thin, perfectly symmetric ring that has about the size that you would expect for the black hole shadow. And this is again just to guide your eye, just to see that these bumps and these minima that you're seeing here are within what we would expect for something that looks like a ring. So let's continue going through the details of how our data looks like. Now we're going to try to understand or specifically build some intuition for why we are so sure that there needs to be a flux depression at the center of our image. So in astronomy, most things are spherical. So if you were to think about what is the simplest possible image in astronomy that I can think of, many people would argue that that simplest image would be something that looks like this, probably a disk. It might be fuzzy, it might be sharp, but it will probably look like this. So the first thing that I want to convince you of is that no matter what you do to the size of the disk, there is no way for you to make a disk be consistent with our data. So this is obviously very significantly oversimplified. This is not how we actually created the images, but again, this is more of a pedagogical argument that I hope will be useful. So this yellow line that you see here, this is the amplitude of the Fourier transform of the image. And all of these red points, those are the actual data that we're using. And so I'm going to change the size of this disk, and you'll see how changing the size will affect this yellow line and whether or not we can make this match these red points. So as you can see, you can change the size of your disk to be able to fit this first minimum that you see right here. However, no matter what you do to the size of the disk, it will be impossible for you to fit the second minimum that you see here, but also the height of this bump here. So there's nothing that you can do with just a disk to be able to create an image that is consistent with our data. So the next thing we're going to try is to add a hole, since obviously you guys have already seen the image. That is a fairly reasonable thing to try next. And now we're going to add a hole. So now you can see that by adding a hole, it's actually very simple to be able to create something that matches the height of this bump and also matches the location of the second minimum. Obviously, this is significantly overly simplified, as I've already mentioned, but again, just trying to build a little bit of intuition so that you can trust us that even just by looking at the data without using any imaging algorithms, people that have been looking at this data a lot already knew that it was going to probably look like a ring. So I also wanted to, sorry, I was not supposed to play that yet. I also wanted to try to demystify the imaging algorithms a little bit. As Marcelo mentioned, I do primarily focus more on the theoretical side, but I did participate in the imaging group as well, mostly because I thought it was a very cool kind of life experience to be in the room the first time that we made an image of a black hole. And so I was part of the group that was using these algorithms to make these images, and so I saved one of the attempts at making an image. So specifically, I saved each iteration from this algorithm just as a demonstration for how this algorithm works. So the idea here is that you have a grid of pixels, and you're going to add or subtract intensity from some pixels and put it on others. And the algorithm will do this, and then we'll take the Fourier transform of that image and compare it to the data that we have. So the images that I was showing you earlier, we only had one yellow curve because the image was perfectly symmetric. And so if you were to look at the two-dimensional Fourier transform of that, it would be perfectly symmetric, and it would only depend on the distance from the center. So you can display all of that information with just a single line when you are doing these plots where I'm showing you the amplitude as a function of distance from the center. However, as you can clearly see, in this image, we do not have anything that is symmetric. And so because of that, one single line will not be enough. And so I'm showing you two lines, and I'm also showing you a gray shaded region. And so we think that, or not even we think, so based on this image, the data could be anywhere between these two lines in this gray region if our data were to be consistent with the image that you see here. So we're trying to iterate to minimize the chi-squared between the Fourier transform of this image and the data that you see here. So let's go ahead and let this algorithm evolve and try to change this image such that it can match the data that we have. Okay, so that was only 25 iterations, and we can already see that the image that you're seeing here is fairly similar to the image that we actually ended up publishing, but also quite consistent with the data that you have here. Also, you need to always keep in mind that there are error bars on all of these things as well. So obviously, when we actually make images to actually publish, we are a bit more careful than the very simplified example I'm showing you here. But again, I'm just trying to demystify the process and hopefully build a little bit of intuition for how we go about using interferometric data to actually create an image. So we used 3 different algorithms in this project. So the algorithm on the top row, that is a clean algorithm for those of you who are familiar with interferometric imaging. That algorithm has been around for a very long time. The 2 algorithms on the bottom here, these are algorithms that are similar to the one that I just showed you. Specifically, the one that I was using on the slide before is EHT imaging, which is the center row here. Each column corresponds to a different day. So we observed M87 for 4 different days. And the point here is that with these 3 different algorithms and for these 4 different days, all of these combinations will still give you a ring with a flux depression at the center. And specifically, you can also see that they all are asymmetric, that the bottom of the ring is always brighter than the top of the ring. Again, trying to show you the details between this versus this. those kinds of details you probably really shouldn't pay too much attention to, because that is just a little bit of variability or uncertainty in the imaging algorithm itself. So we also tried to be very careful to perform several different tests of our imaging algorithms. So what we're doing here is we created 4 different overly simplified models, and we used the exact same algorithms to image these models. So we simulated an event horizon telescope observation and then used the same algorithms to image these. The last example over here is the result of a GRMHD simulation. And so when we try to image these, what is important is that we not only use the same algorithms, but we also use the exact same parameters with each of those algorithms that we used in the plot that I showed you in the previous slide. And so one of the main things that we're trying to make sure that we understand is that we want to make sure that if we were to simulate an observation of a disk, that our algorithms would not result in a ring. That is very important to us. And so as you can see here, our disk model, the disk that you get out after you simulate an observation is a bit bumpy, and that comes from the fact that we do not have a smooth distribution of data points in Fourier space, so there will be a little bit of structure that you will see in your image just from the structure of the actual baseline tracks in the Fourier domain, but you do not get a ring. The other thing that is very important is that if you look at the very first column here, we started off with a smooth, uniform ring, and we took simulated observations of that. And as you can see, if you were to observe a smooth, uniform ring, you would tend to create these little knots that you see here, that are similar to the knots that were in the image that was published in April. So those knots, similarly to the bumps that you see in these disks, we believe that those knots come from the structure of where we see data in the Fourier domain. So again, you should not pay too much attention to the structure of these individual knots. We do not think that they are necessary to fit our data, but they are artifacts of the imaging algorithms. However, if you were to observe an asymmetric ring, like the second example, you do still get an asymmetric ring out, but the asymmetric ring is a bit more bumpy than the original. So in addition to a very strong imaging effort, our collaboration also has a lot of people working very hard on the simulation front or the theoretical front. So I really love this slide just because it gives you an idea of the breadth of the simulations that were run for M87 when we were working on these papers that were published in April. So this is not all of the simulations. Obviously the resolution for this is significantly worse than the actual simulations, but I think it can give you a pretty good idea for how easy it is to create black holes whose images would look significantly different by changing the parameters that we have as free parameters in these simulations. And so one of the interesting things that resulted from this study of comparing GRMHD simulations to the data is this. So here I have 3 different example images. These are from 3 different GRMHD simulations. And I don't know if you can see, but the first one is negative 0.9 spin. The middle one is 0, and the one closest to me is positive 0.94 spin. So the spin is very drastically different between these 3 images. However, if you were to simulate an observation of these 3 images, you would get results that look very similar. So the point here is that you can look at this from a positive point of view or a negative point of view. You could say that if you're trying to look at the gravity and not so much the detailed parameter of the spin, your image is going to depend more on just the gravity and not by the detailed astrophysics, such as how fast the black hole is spinning. Or you can be a little bit more pessimistic and say, well, I really wanted to know the spin, and now we have a degeneracy, which makes it very hard for us to use at least this first observation to actually measure the spin. If you remember, I already explained to you what the black hole shadow is, but now let's go a little bit deeper into why that black hole shadow is important. Specifically, why do we care so much to actually create an experiment to detect the black hole shadow? So the example that I was showing you earlier when you saw the trajectory of the photons, that was for a black hole that was not spinning. That was for a Schwarzschild black hole. However, in space, we believe that actual real black holes will be spinning. So they will be Kerr black holes. And so the obvious first question to ask is, how does the image of a black hole depend on the spin? And specifically what I mean here is, how does the shape of the black hole shadow depend on the spin? And this is different than the images that I showed you in the slide before, because there we also had all of the fluid dynamics of the matter going around the black hole. And so right now you are looking at the boundary of the black hole shadow for a black hole that is not spinning. This is a video, and when I play it, the spin will increase. And so here, the way that I've defined the spin of the black hole, it'll go from 0 to 1. We won't quite get to 1, we'll get very close to 1 though. And once this black hole starts spinning, the spin axis will be pointing up. It'll be spinning in this direction, and you are all observers at the equator of that black hole. So let's go ahead and do that. And you can see how the black hole how the shadow will move over. However, the size and the shape hasn't really changed that much. Only when you get to very high spin do you get a significant deformation in the shape of the black hole shadow. So this is, again, you can look at it from a positive point of view or a negative point of view. I am going to put a positive spin on it because that is what I'm interested in, is using the shape and the size of the black hole shadow to test whether or not this black hole is consistent with a Kerr black hole. So the point here is that if you know the mass of a black hole and you know the distance of that black hole, you know exactly how big the black hole shadow should be, and it will not depend on anything else within about 4%. And so you also know that it has to be very close to a circle. Mathematically, if you were to calculate the asymmetry of this, it is very, very small. So you essentially can use the black hole shadow as a null hypothesis test of the Kerr metric. So you know exactly what the prediction is, and if it's anything different, you know that it cannot be a Kerr black hole. I also, before I move on, I wanted to give a little bit of intuition as to why this thing is moving over to the side, just in case you're interested. If you increase the spin of the black hole, you're essentially increasing the quadrupole moment of your black hole, and so if you were just looking at the effect of the quadrupole moment on the black hole shadow, it would tend to make the black hole more oblate. However, there is another competing effect, and that is this effect of frame dragging. So even though you're making the black hole more oblique, you also have frame dragging. And since the black hole is spinning in this direction, frame dragging will tend to bring photons, kind of shove the photons over this direction. And so these two effects of making it more oblique and then kind of shoving it over, they cancel out almost perfectly. And that is only true because of the symmetry of the Kerr metric. So it's actually not too hard to imagine that if you had a metric that was not as symmetric as the Kerr metric, you might be able to create a black hole shadow that might look very different from a circle, or at most this slightly deformed circle that you see here. So that is one of the things that I've been working on recently, is taking the Kerr metric, adding fairly small perturbations to the Kerr metric, running simulations of what the black hole shadow would look like with that perturbation, with the ultimate goal of being able to use the EHT observations to actually put constraints on the potential size of these weird perturbations that are very theoretical and not super well motivated, but still it's just an initial starting point for us to be able to use these observations to say something useful about if the black hole was not a Kerr black hole, what is the maximum possible deviation that you could have from a Kerr black hole. So these are just two examples. So I'm using a set of metrics that are usually called parametrized non-Kerr metrics. They have a bunch of free parameters. I am probing the full allowed parameter space for each of these metrics. And in each of these videos, I am just allowing one free parameter to change. And hopefully you can see how just changing one free parameter over there tends to make the size of the black hole shadow significantly different. And changing just one parameter over here will create a deformation that's significantly greater than the maximum deformation that you would be able to see with a Kerr black hole. So within the EHT, we also worked very hard on feature extraction algorithms. So the idea here is, let's say that you have now created a large set of images that are consistent with our data using the different data sets, but also using these different algorithms that I mentioned earlier. Now you would like to use these images to be able to measure what you believe would be the size of the black hole shadow based on that image. So there is a significant complexity here because these images are significantly blurred. And so what we wanted to do was make sure that we understood the systematic effect of using these fairly blurry images to actually derive the size of the black hole shadow. So what we did was we created, also as you already saw, a large set of GRMHD simulations. We simulated observations of all of those, and we used the same feature extraction algorithm on those simulations and compared the results that we got by doing the simulated observation and the feature extraction algorithm. We compared that to the known answers, because these are simulations, we actually know exactly how big the black hole shadow should actually be. So this was an effort to understand our systematic error by doing this, and so we are fairly confident that we do have a good handle on what the systematic error is by doing this. But in addition to what I just explained, we also did the full analysis in a completely independent way as well and compared these two results. So this whole other analysis that I mentioned is Fourier domain fitting. So what we're doing here is we're making very simple geometric models, and then we are changing these simple geometric models such that the Fourier transform of these models is consistent with the data. So this is not using the imaging algorithms at all. We are using just the original data and these and comparing the original data to these simple analytic models. So most of the plots I've been showing you, I've only been showing you the amplitude of the Fourier components, but Fourier components are complex. So this plot here is showing you the phase of the Fourier components. The light gray points that are very hard to see, and I do apologize for that. The light gray points are the original data, and these little blue and red squares are the fits. So I'm showing you here two examples of fits. One fit was only using the the closure phase data, and one was only was using both the phase and the amplitude. So again, this is just showing you two completely independent ways that we tried to analyze our data to make sure that we weren't being kind of misled by any systematic issues with any particular analysis method. So we used both the image algorithms and the feature extraction from the imaging algorithms, and also the Fourier model fitting to try to understand how big we thought the black hole shadow was. So this is a summary of all of that. Each of these points is either the result of an imaging algorithm or the result of a model fitting. So the x-axis is showing you the fractional width of the ring that we got from either the imaging or the model fitting, and the x-axis is showing you the mean diameter of that ring. So the black and green images that you see in this black circle here, these are in the imaging domains. These are the results of the imaging algorithms. And the red and blue points that you see here at the bottom, these are results from the Fourier modeling. So it's a very clear distinction between these points down here and these points up there. And I've also added this dashed line here. That dashed line is very important. That is 10 microarcseconds. That is the nominal resolution that the EHT can get. And what is important here is that both of the imaging algorithms that I'm showing you in this plot are constrained such that they will not create any structure that is smaller than 10 microarcseconds. So it is impossible for you to use those images, those imaging algorithms, to create an image that would be below that dashed line. However, we do not have that constraint in our Fourier model fitting, and so it is fairly simple to create Fourier models that are below that dashed line. And you can also notice that I've shown here these two shaded regions. That is showing you a correlation. This is a analytical, theoretical correlation that we expect to see from images that look like crescents. And so it's very well understood why all of these things lie on this line here. And it is what we would have expected. However, if you were to look at the full range of all of these points on this x-axis, you can see that even though we are using completely different models, the range of errors, if you will, for the actual size of the ring is still fairly small. And so we can confidently say that the image diameter is 42 plus or minus 3 microarcseconds, that the ring width is less than 20 microarcseconds, that this parameter gm over dc squared, which is really a proxy for the mass, so if you know the distance you can then use this parameter to solve for the mass. So this mass, according to the images that you're seeing there, the mass that we derive is 6.5 plus or minus 0.9 times 10 to the 9 solar masses. So the next step is comparing the mass that we derive to previous measurements. So I keep pressing the button too many times, and I do apologize for that. The dashed red line here, this is the result that was derived using gas dynamics, and that is from Walsh et al. 2013. The blue dashed line is derived from stellar dynamics, and that's from Gebhardt et al. 2011. And so before we even consider what the EHT measurement is, it's fairly clear that these two measurements don't necessarily agree with each other. And so there might be something weird going on with one of these measurements, or some kind of systematic that we might not completely understand. So if you were to compare the EHT measurement, you can see that first, this kind of purple line that I'm showing you here, these are the results using the analytic, like geometric models compared to the Fourier domain. The green area, this is the result that you get if you try to fit GRMHD images to your Fourier domain data, and the blue is what you get using the imaging algorithms. First, all three of these different independent algorithms or methods do agree with each other, but they also all agree with the results from Gebhardt et al. 2011, which was using stellar dynamics. So you could potentially use this result to try to maybe argue that there might be some sort of systematic in that the gas dynamic based measurement from 2013, and maybe we can use this as a third independent measurement to be able to kind of resolve this discrepancy between these two measurements. Another thing that you can do is you can see if what you are seeing in this black hole shadow is consistent with what is predicted with Kerr. So what we're going to do here is the following. If you assume that the stellar dynamics measurement, if you were to assume that that measurement is correct, is the black hole shadow that we measure consistent with what would be predicted for Kerr? And the answer is, of course, yes. So here we have the distributions of what is measured from the gas dynamics and the stellar dynamics in the same colors as before, and this little very light blue line here, that is what the measurement would be in the black hole shadow if the black hole was a Kerr black hole. And so as you can see, the stellar dynamics measurement is completely consistent with this black hole being a Kerr black hole. However, if somebody could prove that actually the gas dynamics measurement is the one that is correct, then this might not be a Kerr black hole. So that is still a little bit uncertain. We do believe that the stellar dynamics mass is correct, but there is still a little bit of wiggle room that as we observe different black holes and as we continue to observe black holes with a better instrument and better algorithms, we might be able to learn more about whether or not this is really a Kerr black hole. So the other thing that you can see, or the other thing that you can try, is you can look at the shape of the black hole shadow. And you can determine whether or not the shape of the black hole shadow is consistent with this being a Kerr black hole. And so the idea here is the following. We're going to compare the largest diameter of the black hole shadow from several different images to the smallest diameter. And so what I'm plotting you is the ratio of these two. And so all the red histogram is images that were created using the EHT imaging algorithm, which is the imaging algorithm that I used to give you that example that we saw the image be iterated as a function of time. Whereas the green histogram, these are the results using a different algorithm that is similar to that one, but it is an independent algorithm. It's called Smiley. And so first we can see that all of these images are both algorithms are fairly consistent with each other. All of them have very small asymmetries, but what I think is really important is to take into account this blue region over there. That is our resolution limit. And what that is saying is that even if we were to observe a perfect circle, we would not be able to constrain the fractional deviation between two different diameters better than this limit right here. because we don't have enough resolution to constrain it better than that. And so the fact that these histograms peak very close to the resolution limit right there shows you that this is, at least so far, completely consistent with a Kerr black hole. Specifically, we can say that the maximum deviation that we've seen in any of our images is of about 10%, which is greater than what you would expect for a Kerr black hole, but given the overall distribution of these images, we again think that this is perfectly consistent with a Kerr black hole. So I'm going to shift a little bit and talk a little bit more about my own research and also talk about the future. So I introduced to you two black holes, and I said that we want to observe both of these black holes, and that both of these black holes should have about the same resolution using the EHT. So why is it that you have not seen an image of the black hole at the center of our galaxy yet? So this is, again, the result of a simulation. And what is important here is that this thing is incredibly variable. And so what is important to remember is that this black hole is about 1,000 times smaller than the black hole in the center of M87. And that is, again, not a problem for the resolution because this black hole is very close to us, but it is a significant problem for variability because the time scale for variability for black holes or accretion systems like this scales with the mass of the black hole. So if a black hole is 1,000 times smaller, it'll vary 1,000 times faster. And this is a very big issue because I've already explained to you that it takes us about 12 hours to be able to collect enough data to actually be able to make an image. So during those 12 hours, the black hole at the center of M87 is perfectly stationary. It's practically posing for the picture. However, the black hole in the center of our galaxy is expected to be very variable. For example, we've seen flares from Sagittarius star, specifically in the X-ray. We've seen flares where the total X-ray flux changed by a factor of 1 or 200. We've seen events like that within 1 or 2 hours. So we know that this black hole can be variable within timescales of 1 to 2 hours. And so that is significantly smaller than the 12 hours it would take for us to collect enough data to actually create an image that is using the algorithms that we've already developed. And so let's go a little bit deeper here. This is, again, more of my own research, and try to understand what is really happening with this variability, specifically in the Fourier domain. So this is the exact same simulation that I just showed you. The rest of the talk will be focusing on this simulation for consistency, and I think it's just simpler that way. So here you are seeing the image of this simulation vary as a function of time. The middle panel is the two-dimensional Fourier transform of that image. However, I also wanted to show you images that are kind of similar to the images that we've been looking at. So instead of looking at the full two-dimensional map of the visibility amplitude, I also wanted to show you vertical and horizontal cross-sections so you can see what the curves look like and hopefully remember where the data points that we had seen for M87 would look here. Before I forget, all of these white lines, these are the baseline tracks that the EHT would get with the same array that was used in 2017 for Sagittarius star. So it is a different baseline track map because the baseline track map will depend on the source. So if you have a source in a different area of the sky, different telescopes will be able to see it, for example. So the information here is essentially just the vertical cross-section of this image and the horizontal cross-section. And of course, the point that I'm trying to make here is that the variability that you see in the image is very, very, very significant in the Fourier domain. And specifically, the location and the depth of the minima that you would hope to be able to use to actually create an image in the Fourier domain, that is incredibly variable. So how can we possibly hope to use data from this black hole to be able to make an image if the Fourier space could be doing this during the 12 hours that we are observing? I didn't mention, so the timescale here, I believe this entire video is about 1 minute, and that corresponds to 60 hours. So 1 second here of this video is about 1 hour. So 12 seconds would be the amount of variability that we would expect to see within a single EHT observation. So very significant variability expected from this black hole. So the first thing that you might want to do when faced with something that is variable is take an average. That's a very obvious and very reasonable initial attempt. So is it okay to just take the average here? So a Fourier transform is a linear operator, and taking the average is also linear. So you would expect that these two things would commute just fine. However, there is an important complexity that we have not dealt with, and that is the fact that we are not dealing with the full complex numbers, but we're dealing with the amplitudes and the phases separately. The reason for that is because the water vapor in the atmosphere will affect our phase measurement. And so we can't actually determine absolute phases from our data, so we have to use closure phases, which are the clever addition of phases at 3 different telescopes. The point of all of that is just that this is no longer linear. Because what we would actually be doing is we would be taking the average of the amplitude of the Fourier transform, and then we would separately be taking the average of the phase. And that will create something that will not be linear. So I have an example of that here. So this, So this first panel right here, this is what you would get if you were to take several different images, take the Fourier transform of each of those images, take the amplitude of each of those images, and then take the average. Okay, so we're going to call that the mean of the visibility amplitude. The middle panel is what would happen if you were to take a set of images, let's say the same exact set of images. You're going to take now the average of all of those images, and then you're going to take the visibility amplitude of those images, of that average, I mean. And as you can see, these two things have very different results. And specifically, you get a lot more kind of information in this middle panel than you do if you were to just take the average of the visibility amplitude. And so as previous plots, I'm also showing you vertical and horizontal cross sections of these two so we can compare them more precisely. And so the solid lines correspond to the leftmost panel where we're taking the mean of a bunch of different images that have already been, where we've already taken the Fourier amplitude of those images. And this dashed line corresponds to this middle panel. So if you remember when I was showing you the very simple kind of intuitive examples of having a disk versus having a ring, we were focusing a lot on these minima, right? And the minima, at least historically in VLBI, have been very important. People tend to try to interpret those minima a lot. But if you were to take the average, you will essentially completely erase the information of the location as well as the depth of that minima. And you will essentially end up with something that is almost monotonically decreasing. And the reason for that is that when you are taking the average of several curves that have minima in different locations with different depths, you will tend to just smooth over all of that information. Whereas if you have a bunch of minima that are in the same location of different depths, you'll still get a minima in that location. So the fact that the GRMHD simulations predict the location of the minima will change is very significant here. So we do not feel that taking the average of the visibility amplitude data will be enough to deal with this variability that we expect from this black hole. So the other thing that we're trying to do within the simulation is also compare our data to the simulations that we have. So hopefully I've convinced you that just taking the average of the data will not be enough. But you might still be thinking that, okay, that's fine, but at the very least you can only use the average image from each simulation, and you can compare the average image from each simulation to the data that you have. So, again, we are looking at the exact same simulation I've been showing you the past few slides. Here is the average image of that simulation, and here I'm showing you 3 different snapshots from that same simulation. And the point here is that if the EHT were to observe a black hole that looks like, let's say, this, so we're going to observe a black hole that looks like this, and then we would like to compare that to GRMHD simulations. We would compare that to the average image, and we would see that these two things are not consistent with each other. So by doing a fit like this, you would not only potentially get completely wrong fit, but even if you got something that worked, you would still be very suspect about your parameters that you had derived from doing that. So as an example, in the papers that we published in April, instead of comparing things to the average image, we actually went through and compared our data to each and every individual image within each of these simulations. That is a reasonable first step, but I think that we can do better, and I'm going to try to convince all of you of that as well. So I am currently working on an algorithm that uses principal component analysis. I'm sure many of you have heard of this, but if you have not run across this algorithm yet, I'm going to try to give you a little bit of a very fast explanation of what this algorithm is doing. So principal component analysis, or PCA, diagonalizes the covariance matrix to find an eigenbasis that is ordered such that the first few principal components explain the majority of the variance. If that just sounded like a lot of words and you've already been listening to me talk for a long time, don't worry, because I also have an example. So let's say that you have a set of data points that look like this. And now you want to take the PCA of these data points. You would do that and you would get two PCA components that would look like this. So this longer arrow right here, this would be your first PCA component. And that first PCA component will be aligned in the direction of the majority of the variance in your data set. The other principal component will be orthogonal to the first. So we're going to build on that. I am going to be applying PCA to images, so that will be a little bit more complicated. So I also have an overly simplified example of what happens when you take the PCA of a set of images. And so the top panel that I'm showing you here, this is going to be our simulation. This is literally just a Gaussian going around in a circle. The red circle is not actually part of the simulation. That's just so that you can see what the orbit of that little Gaussian is. If you were to take the PCA of this set of images, you would get these PCA components. So there are many others. I'm only showing you the first four. The very first PCA component will just be the average of that simulation, and the others will hopefully give you a little bit of an idea for how PCA works. Because the idea that I want you guys to be thinking about right now is the following. You can use a few PCA components, you can make a linear combination of these PCA components, and you can get a fairly good approximation of any of the images that are in your original set of images. So if, for example, you knew what accuracy you needed in your reconstruction, you know that you need to be able to reconstruct these images to some accuracy. Based on that accuracy, you can then decide how many PCA components you need to be able to do this. And it's very frequent that you can do a very significant dimensionality reduction by using PCA. So I applied this to that same simulation that I've been showing you all along, and these are the results. Like the overly simplified model, this first image here is just the average of the simulation. But if you look at these images here, this very second PCA component is just showing you that that region that is shown very in black in that second component, that region tends to change in brightness a lot. And if you compare that to the simulation at the top, you can see that that is, in fact, one of the ways in which that simulation is changing. Something else that's very interesting is this structure right here that is also present in this PCA component. What is actually happening here is the following. This black hole, the spin axis of the black hole is actually inclined towards you at about 60 degrees. And there is a funnel region. It's not really a jet, but it is a region that has a very strong magnetic field, very low density. It's not actually expelling that much stuff, but regardless, we call it the funnel region. And what you're seeing in that structure is that the very edge of the funnel region sometimes lights up. And so that's, again, one of the ways in which this simulation can vary. So the idea is that you can use a linear combination of PCA components like these to reconstruct all of the images that are in your original data set or your original simulation at the top. So, of course, I did actually do this. So that very first image on the left there, that is just an example snapshot from that simulation. That is the original snapshot. The next panel over, that is showing you what that snapshot would look like if you were to use just the first 10 PCA components to reconstruct that snapshot. And obviously we are losing a lot of the fine scale structure of that original image. However, if you were to compare this to the size of the EHT beam, you can see that this is actually doing really, really well. This is well above the minimum accuracy that we would like to have when comparing reconstructions like this to the EHT. So I can say that given the size of the EHT beam, I only need about 10 eigenimages, which is a significant dimensionality reduction because I started with over 1,000 images in the original simulation. Obviously, if you use more eigenimages, you'll get more of the fine scale structure. We don't really need to worry about, at least for the current instrument that we're using. And so the idea, or the algorithm that I am proposing here is the following. I'm going to, or I currently am, creating a very large set of GRMHD simulations, trying to probe as much of the allowed parameter space as possible. And then I will apply PCA to this large set of simulations. I will get a set of a few principal components. And then we can actually use those principal components and we can create a linear combination using those principal components that can be consistent with the data. And because we're just fitting, essentially, in this example, you would only have to fit pretty much just 10 numbers, which are the 10 amplitudes for all of these principal components. It's a much easier problem to solve than using the imaging algorithms that we used for this first announcement. And so you might be able to do this without needing all of the 12 hours of observations. You might be able to do this with half an hour of observations, for example. And so there are two important things that I think we are gaining by using this as opposed to doing the things that we were doing in that first publication. So first is the following. So when we are doing this, we are obviously saving a lot numerically. So you are just doing one fit, and you can compare, essentially, by doing that one fit, you would be able to reconstruct all of the images in your original data set. So you can create an original simulation data set with 1 million images, and by just performing a single fit, you could compare practically all of those images to your data to see if there's any image within that original data set of 1 million images that could be consistent with your data. The second thing that we're doing is that you can actually also create images that are not contained in your original data set. So if you think about this from a geometric perspective, each of these images is essentially a vector somewhere in this weird hyperdimensional space that these images can live in. So all of these images that you have, let's say you have 1 million images, you have 1 million vectors. All of these vectors are going to occupy a space, okay? But they might not be completely filling the space, or they might also not be evenly distributed within this space. By using an algorithm like this, you can create an infinite number of images that are contained within this broad space that these images live in. You are not constrained to only create images that are within your original data set, but you'll be able to create images that live in the same general area of parameter space as these images. And so with that, I would like to leave you with my summary. We have detected the shadow of a black hole for the first time. The size and the shape of this shadow is consistent with the predictions of the curve metric. Both imaging algorithms and analytic models were used to fit to the data. We can use this observation to measure the mass of the black hole. And finally, the variability of Sagittarius star poses a significant challenge, and I am trying to resolve that challenge by using principal component analysis.